Welcome to episode 101 of AU Manufacturing Conversations. No vision is realized without innovation and collaboration, and today's podcast sponsor, APS Industrial, understands this as much as anyone, providing exclusive access to the market-leading Siemens Industrial Automation and low-voltage electrical portfolio. APS Industrial partners with the best to bring local industry the best. Take the newly released Siemens Cynamics G220 high-performance variable frequency drives. Designed to meet current and future challenges in every industry, Cynamics G220 takes digital drive technology to a new level. Cynamics G220, the drive for tomorrow, brought to you today by APS Industrial. Now on with the show. Steve Camilleri, thank you for joining us again. Welcome to the program as the only third-time guest of AU Manufacturing Conversations.
Yeah, thank you. That's a wonderful honour. Yeah, great to see you again. Yeah, I've thoroughly enjoyed every activity we've had together, so looking forward to this one too.
They've been fun, and I'm sure this one will be too. Something that seems timely, and we were just talking about, is that you're almost a decade old as a company. I've sort of kept tabs on you guys at a distance mainly for the last few years, and wow, 10 years already. Tell me your thoughts.
Well, yeah, I mean, firstly, that's a bit of a confronting idea. I hadn't really thought of it until you mentioned it, which just kind of communicates how busy we are, that we're not thinking about this stuff. But yeah, this is a milestone that we should celebrate at the company. There's been a lot of work that we've successfully completed. A lot of really interesting technologies emerged. We've had a huge amount of fun. Working very hard, using your brain and being successful has got to be one of the most rewarding things you can do. I think personally, for me anyway, and for a lot of people at the company as well. But yeah, we just kind of lose sight of some of these larger milestones when we're so busy focused on what's happening day to day. So thanks for reminding me of it.
Don't mention it.
Yeah.
Another milestone that you may or may not have kept tabs on is the number of machines you built. I mean, last time we spoke, I think you were at 50-something. What can we say now is the number of machines?
Yeah, so it's been a very big year. So I don't actually know the current number. We're building machines every day. But last I heard, we were approaching the 100 milestone. So that's another one to celebrate, I think. I think in tech startups in particular, your 100th product shipped is one of those milestones that, again, some high percentage of tech startups never get to. So it's nice to be in a position where we're feeling a little mature. So let me enjoy that moment. That's a moment I didn't realize we were coming across, but there we are. It's wonderful.
There you go. Another thing I'd like to get your point of view on is the idea of, some people call it massive transformative purpose or a similar buzzword. It can go by other names, but you guys seem to have had a sort of vision of, as long as I've been looking at you, to be competitive with cast parts while printing metal, which years ago would have seemed an insane thing. Tell me about the importance of that vision.
I think that having a really strong vision is an essential requirement in a tech startup. It's too easy to say, we have a cool tech, people should just buy it because it's cool. And it's too easy to say, we want to work on this, other people should value it because we value it. I think a lot of tech startups are guilty of those particular misinterpretations of what the world wants. You've really got to look outside and understand what it is that people need of you. So ultimately, we're all in technology companies, manufacturers. We've got to do something that improves someone else's day. If we're not doing that, why are we here, right? Nobody really cares how fancy our new laser is. It's got to be doing something for someone. And so that vision has to come from understanding what the real world problem is. And I think I would certainly recommend to any tech startup who are contemplating, if there's a worker in a government office right now listening to this and they've got a brilliant idea and they're wondering what it really means and whether the world will care about what they might do, I would encourage them to think very deeply about what problem exists in the world that they're trying to solve. Why should people be interested in what they're doing? And the vision statement comes from this important information. So you just got to keep asking yourself over and again, why and why? Why is this important? Why do people care about that? Why is that important? What does this all mean? And eventually you get to this point where you say, in our case, it was, metal casting is great most of the time, but when it's not great, it's especially not great. So a lot of people are having to make parts in campaigns, in facilities that are designed to do campaigns, short run, low quality, low performance, high cost, and they're retooling these facilities every week or month to make different geometries. That's just the default. That's the best way that we currently have for making parts like that. We came from that industry. The world deserves better, and 3D printing looked like it would solve the problem. So that's why we thought, let's try and resolve this problem of casting. We think people will be engaged with that. And in fact, what we've really found, so that vision statement is now due for a revision, because what we've found is it's actually the users of the parts that are more inclined to think about the new technology solution. So when we've got people that are, that have serious jobs that make big, important pieces of equipment that nations need, and they can't get the components that they could 20, 30 years ago the same way. The facilities don't exist anymore. People have moved away from the industry. It's become less sexy, less interesting. It doesn't attract young people, high levels of skill, and they just erode and they disappear with a whimper. Casting is suffering from this very significantly around the world at the moment. So we just happen to have lucked on this much more important question of what are people going to do when they can't cast the part anymore? Because at that point, there are really no good options. And so we found that to be a much more appealing solve, but we wouldn't have got there if we hadn't tried this first one of let's make casting a little better for people using 3D printing tech. And now it's all about let's get you those parts that you can't get.
On a dollar basis, once you do the maths, how close do you think you are to being competitive with casting, and for what volumes?
Yeah, it's a good question. So I do ask myself this question very often. So Byron and I have a manufacturing background. We're a bit weird. I think we've spoken previously. We're academics that were trained to build factories, which is a pretty weird thing. We're very good at understanding what the inputs are to a costing. The challenge here, I think the very first question you need to ask yourself is, what's the apples to apples comparison to make? So if you've got a very successful high volume casting operation at, a company like Toyota or something like that, and every day you're making this huge volume of stuff and you've got a whole team of people dedicated to making sure those tools are sharp and, the processes are being carefully measured. And every day, the slightest deviation, there's someone in there with a screwdriver tweaking it over. And, you're making stuff at high volume with very, very high quality and very, very low cost. You've got to ask yourself the question, why would you want to make a process that competes with that? That's actually pretty well as optimized as anything that humans do is optimized. There's no point competing with that. In fact, I wrote an article for Metal AM magazine maybe 18 months ago talking about how actually you've really got to find the right kinds of stuff to 3D print. And that stuff, the stuff that Toyota make running 3 shifts a day in high volume, is just a bad application of 3D printing. The process they have now is great. There's no problem with that casting process. So it's, as I mentioned, these problems of campaigns and short runs and parts suddenly needed that haven't been needed for 10 years out of complex materials, complex geometries. This is where you really have huge opportunities for 3D printing because those guys don't have a lot of choice in their solution. So solving their problem is important. Now, if you want to compare the cost there, we are streets ahead. So we will typically make a part. So if it was us costing our process, this isn't necessarily any of our customers and their process, but if it's just us saying raw inputs, here's what the process looks like. You're looking at the material kind of in the $100 to $150 Aussie a kilo. There are cheaper materials than that. It depends on the material.
Yep.
And you're looking at a process cost done in that kind of way, intensively, of about $10 a kilo. So sort of sub 200 a kilo, even worst case. So you'll find that campaign casting typically costs $250 to $350 a kilo. And this is for mediocre stuff that doesn't look great, doesn't have good material properties. But people have retooled a factory, a casting facility to make this stuff, make 2 tons of it, and then switch it out for another tool. So we make parts with better properties, far more predictable, faster, with low cost. That's been true for some time. So you got to make sure you're comparing the right apple to the right apple. But I would say we've been well north of casting for some time in terms of performance. So the right tool for the right job.
Right. So we're here at Land Forces, and you have on display the honking new machine, the EMU. Tell us about what EMU does and why it's out there.
Yeah, so EMU is an acronym, Expeditionary Manufacturing Unit. So it's 2 20-foot shipping containers. One of them does all the printing and the other one does all the post-processing, so heat treatment and machining and testing and design. There's a little bit of a story attached to the development of this thing. During the pandemic, we probably spoke about this a little last time. We got called up by the Australian Army, who were very keen for us to explore the idea of solving some supply chain problems they had during the pandemic with the additive manufacturing. And we learned a lot about what they really needed through that process. So I went out field 4 times. I think I might have mentioned that as well. For those who haven't met me, I'm a pretty overweight and pasty kind of engineer. Going out into the field and digging a hole and sleeping in it and eating rations was an experience. I enjoyed it far more than I usually like to admit to. But we learned about their context. Tech companies usually struggle to do this, and I'd advise tech companies to take every opportunity they can to learn about the context of their customer. So we had this opportunity. It would take us out into the field. They would show us about the problems they had and the environment they had to be compatible with. And we thought, man, there's a lot of people thinking about AM in the field, expeditionary additive manufacturing. And just buying a product off the shelf and sticking it in a box It doesn't work. There are so many requirements here that aren't addressed by that kind of oversimplified solution. So, how is the material being stored against humidity, rain, insects? Insects turn out to be a big problem in the field. How are you dealing with noise for people that want to be concealed? How are you being compatible with the way that power works in the field? Interruptions, refueling. These are all quite novel problems for additive manufacturing. This is not something that people normally have to worry about. How do you do high quality metal parts in the field when we don't have access to inert gas? So most metallurgists would tell you it's very difficult to make good quality material without inert gas. But because we're cold spraying, we're not heating the material significantly during the manufacturing process. We can get away with using air and still get excellent material properties. The EMU is the answer to that problem. So we have a 3D printer, a metal 3D printer, cold spray technology based, where all of the different peripheral bits of equipment, so dust extractors and compressors and little storage areas, the robot controllers, all of that stuff is integrated into one shipping container. So this is a huge advantage because not only is it easier to move around because it's just one box, it's easier to deploy. So what that means is it's faster to deploy. So when you think about the requirements that the Australian Defence Force has now to be littoral, this idea of being able to move between land and sea, get ashore, set things up for a couple of weeks, do some stuff, get back on the ocean, go somewhere else, do it again. Being that deployable is quite important. We needed our infrastructure to be compatible with their infrastructure in terms of moving it around, setting it up. We needed to be compatible with their people. So Australian Defence Force has this another acronym. It's called FIC, Fundamentals into Capability, which is all of the different inputs that go into actually knowing you have a thing. And there's a lot more than just the physical having of the thing. Like it's how do you staff it? How do you command it? How do you restore it? How do you keep it sustained? So it's quite a good philosophy, actually. We're pretty good at this philosophy stuff in Australia, I reckon. And so we've used that philosophy to define how this EMU system is operating. It's all designed to be easily trained, implemented, like soldiers can use it, sailors can use it. They can make the parts they need. Most importantly, they can be certain the parts are right as well. So we've been developing the procedures and the validation tests so that in the field you can make something very fast and actually know that it meets the requirement you have. You're not presenting new risks to people who might be using the parts.
Designed to meet current and future challenges in every industry, Siemens Cynamics G220 takes digital drive technology to a new level. Cynamics G220, the drive for tomorrow, brought to you today by APS Industrial.
In one of those two shipping containers, I noticed a bit of equipment that looked an awful lot like something made by a wonderful company I visited yesterday that makes thermal processing equipment. You probably can't say the company's name, but they know who they are and they do wonderful work.
Yes, I do.
Would you like to say how they came across your radar and the presence of obscure but very capable companies that exist in your supply chain?
Yeah, this is a really interesting point. We have this confidence problem in Australia with our manufacturing sector. I think we drove a nail into that coffin when we terminated the automotive industry. People are still in trauma recovery mode from that. But the reality is we have a lot of very clever companies doing a lot of very clever stuff in Australia. We don't especially celebrate it and we don't especially celebrate them. But they do it anyway because they love doing it and they're very good at what they do and they compete on a world stage. We're actually quite comfortable. We build the printers in Melbourne. Our supply chain is healthy. We have a lot of companies that we work with that make really cool tech that we've integrated into ours, made part of our system, part of our process. And we love working with them. They're fantastic people. They're very clever. They're doing world-class stuff. So, I think our reliance on the Australian side of the supply chain, I'm quite happy to celebrate and acknowledge. I think that's an important thing. I should do everything I can with the position I have to encourage people to be more confident about what we do in Australia. I think that's a very important thing.
Yeah, I can only nod.
Yeah.
So lastly, you guys have a pretty aggressive development schedule. It looks like you're bringing out a new machine, pretty regularly, and features for machines and software and other odds and ends. You're currently working on Titan Speed. What is Titan Speed, and is it just a bigger machine for the sake of making a bigger machine? Yeah,
this is not a very good question. The reality is that of all the stuff that humans need to make, large parts, I would say, are some of the hardest. If you look at how a ship is made, so we will cut the ship up into segments and we will make the segments one at a time and then we'll build it up like Lego. You look at how spacecraft are made, it's very similar. The reality is that we are a particular size and shape as humans, as biological entities, and we tend to think about the problems in the scale that we are used to. So I imagine this is why people get so excited about things like nanotechnology, is because that's well beyond the scale that we're used to, right? So if you go the other way, if you go big, every time people start talking about something that's large that needs to be made, it's all about a giant construction project, right? It's a fabrication project. 3D printing is really interesting, pushed into that space, because we have this, ferociously helpful ability to automate a lot of the manufacturing process with 3D printing. So the idea of giant 3D printers that make giant parts, it's actually quite appealing, because one of the default mechanisms that you make large parts by casting is a thing called pit casting. Basically a giant facility, big hole in the floor, and people will custom make a sand pit with a negative of the part in the middle of it over weeks, usually, digging and troweling sand around like Zen masters, building it around this part, and then they will pour the molten material in, and then, pray to whichever gods they believe in that factory that the part doesn't crack as it's cooling down. And if it does, can they weld it up? Can they make it good? And if they can't, melt it and start again. That's pit casting. And a lot of our big parts, even for our very advanced platforms like ships' propellers, are made this way by default. So, I don't want to kind of demean the people who do that work. I mean, it's fantastic work, but it's a process that's fraught. You can't really be certain about the qualities of the part that you've made. You've got to over-engineer. It's very hard to test those parts. And, your likelihood of success, the predictability of the process is low. So for that to be the best that humans can do, like I'm a Star Trek fan, that doesn't feel right to me. I think we should do better. And I think 3D printing or additive manufacturing is a real opportunity here. Now, one of the problems with scaling up other technologies, a lot of metal additive technologies are thermal. So they're melting the material, placing the molten material on the part in the place where it needs to grow, and then cooling that part down and then adding more later. The problem with that is thermal expansion. So as you heat and cool the material, it grows and shrinks, and you end up inducing stresses in the part, and most importantly, the part moves around as you're building it. So it becomes very, very difficult to make large stuff that way, because all those problems are compounded. It's just a scale issue. If a little tiny part only moves around a tiny bit as you're heating and cooling it, that's fine, right? You can deal with that. So laser powder bed fusion is very good at the small parts for this reason. But, DED process, and I think our process is essentially a DED process, struggle with large parts because if you're melting and solidifying the material every time you apply it, that's moving around like a snake as you build it up, and becomes very difficult to put the material in the right place and have the final geometry be right. Cold spray doesn't have this problem. We're putting the material together cold, room temperature, essentially. We get very, very little thermal movement in the part. So that makes large scale much, much easier than it does for other processes. To be honest, we've kind of bowed to the market demand for this one. So it's mostly US DoD, very interested in making large parts. The supply chains they have for making those large parts are strained for these problems I've mentioned about casting. So they want something that's more robust in terms of being able to deliver the outcomes they want. So cost isn't really a huge issue. Time actually isn't really a huge issue. Just the reliability of the outcome is the issue. So, we've thought about it. It's like, scale the technology up, everything gets harder. It's going to be a fairly expensive, fairly twitchy kind of process. But then you look at the other ways that people make parts like that, and it's like, wow, we are streets ahead, in fact, in terms of complexity, reliability, cost, performance of the part. So we've had to be convinced by people that this is a way we should go, but we've been convinced. There's real opportunity here. Now, what I want to talk about is space as an application.
Go.
If we're going to go to space, if we're going to colonize the solar system, have places, holiday destinations on Pluto, we've got to figure out how to do manufacturing in space. The idea of everything that humans will ever need being made on Earth and then shipped up through the gravity well, that's not going to happen. We've got to figure out how to do manufacturing off planet without the supply chain that we have here. So I think that scale is going to come very naturally and very immediately once we start thinking about AM in space. A lot of the kinds of parts that we're going to need in space are going to be things like seam-free pressure vessels, so we can put people inside, they can breathe. Oxygen tanks, fuel tanks, large engines, large latticework structures for supporting, for being mechanical supports. This might be on the moon, it might be in the orbit of the moon, might be on Mars, might be in the orbit of Mars, who knows, right? But if we don't have good quality metal additive manufacturing that can take the feedstocks that are available in those places, process them and turn them into components that humans can use, we're not going to succeed, right? It's just too hard to bring all that stuff up from Earth. So whenever I'm thinking about large additive, I'm trying to address the needs in the room for the people that I'm talking to. But my long-term vision is, how do I make the perfect space printer? How do I make sure that by the time people are talking to us about putting manufacturing capacity on the moon or in the orbit of the moon, in the Gateway station that's coming up, that we're the default answer because our process is the right process. And so, I mean, fundamentally, you've just got to be able to make a giant pressure vessel by additive manufacturing, and I think you'll win that. That's my personal view, because those are very hard to make and very important to have. Large additive, I think, is a totally different market to the additive that we all know and love. You know, a lot of additive processes right now, you can tolerate the idea of making a part and it doesn't work and you try it again. If you've just spent the last 3 months making a 5-ton part, no one's going to do that, right? You've got to figure out how to make that right. So how do you get the qualities and the reliability of the process up to these stratospheric levels that you can make these large parts stop when you found a problem, detect problems, react to them as you go? How do you handle these giant parts? It's a totally different issue. I mean, I could build, even with our Titan system, I could build a part that was sufficiently large and weighty that if something happened and it cracked while it was printing and it landed on one of us, it would kill us. So that's not a problem with your average, Officeworks FDM printer. This is a new problem. And, if you've got to get to a high level on the part and do some rework, you're talking lifting platforms, overhead cranes, you heat treat these parts and they might be too hot to go near. They might be radiating terminal levels of heat for weeks. So, how do we manage that? We don't have to manage that now. These are all kind of new problems for the industry. So what I've got to make sure that additive doesn't catch these problems as a new problem. Like, it's not because of additive, it's because of large scale that we have these problems. There's a lot of demand for large parts. It's growing. You look at all the needs of defense, mining, energy, even renewable energy. See the size of wind turbines that are being made now. Like, large scale additive is a natural thing that must happen. We just don't think about it often as humans because it's outside of our scale. But the reality is that the problem statements are already right there, and we've decided to go after it for that reason.
When can we expect to see this very large printer?
Yeah, so we're beta testing it now in the US with some of the DoD customers that we've been talking to, and they're going to prove that it'll solve the problems they have, or it won't, in which case we'll solve the capability gap and we'll fix that. We'll get it all sorted out. So yes, we're anticipating maybe a year or so before we start rolling these things out more wholesale. And of course, that won't be for everyone. There's not too many people that'll be able to kind of deal with the infrastructure requirements of large parts. It's one of those markets where there isn't really a good solution now. So I'm kind of tentatively expecting there might be a huge amount of interest in this, but people would need to kind of recognize that the old problems they're dealing with every day they thought were unsolvable, maybe now could be solved. So that's kind of the marketing challenge with that platform, is how do you tell people that actually there is hope now? There wasn't yesterday, but there is now. That's a hard marketing challenge.
Sure. And how large would we be in terms of large? We've just said the word large. What would the platform size be and the size of the objects? Yeah,
so we're talking about a bit over 2 meters in diameter, a bit over 2 meters tall. So if you were to fully fill that with material, it's order of 100 tons. So I don't think we're talking about going there with the weight. The weight is probably going to start out several tons and move up to tens of tons because, there are all those complexities of making large parts that I've mentioned that need to be resolved. But, I'm hopeful that the system as it is kind of conceptualized now will actually be capable of solving some of the problems, these intractable problems that people have now. And of course, we'll be able to make it do more as we learn more about the problems that people want to solve. I imagine there probably are other 3D printers that are promising that sort of size and scale, but we're actually making the parts already. So I think one thing I found is, other than outside of wire arc, which seems to be really kicking goals in large scale, there aren't a lot of people who are telling you about successes they've had with large metal parts in additive.
Yeah, that would be the one I would mention if someone asked. I don't think I've seen cold spray scale up to large, and certainly not laser-based methods. They tend to be of your implant-type sized things. I've seen a hypersonic jet made in many parts out of laser additive, but on the whole, it seems to be limited to wire arc.
Yeah, we're quite complementary to wire arc with what we do. So wire arc's very good at what they call weldable metals for obvious reasons. We're very good at non-weldable metals. Cold spray really doesn't care how weldable the material is. So we can do all that exotic stuff, aluminum alloys, aluminium alloys, copper alloys, titanium alloys, that wire arc finds a bit challenging. In 10 years' time, if I was setting up a facility and I needed to provide to government and industry large-scale parts in a variety of ways, I'd want to have wire arc and cold spray technology.
Well, it's been fun having our, annual catch-up.
Indeed.
It seems to fall this time of year every year. And, look forward to the next one. And congrats on a decade.
Yeah, thanks very much. Yeah, appreciate it.